you realize, well, I expected this to be different because it was from someplace else. It was a different environment in Sumatra. Now, does that one sip of coffee tell you everything about the weather in Sumatra and the soil and the people who harvest the coffee? Bless them. Of course not, but it's different, and yet it's still coffee. And that's what we have in this case. We have a cometary body. It behaves, it resembles the homegrown comets that we have in our solar system, and yet it's excitingly different in particular ways. It does the same thing comets do. It evaporates carbon dioxide gas, it evaporates water. But it's evaporating more carbon dioxide compared to water. So that's a very interesting thing. Comets evaporate dust, and the dust is broken down. The minerals are broken down by the ultraviolet light of the sun. And comets, we know comets put out nickel, they put out iron. That's what comets do. This particular one is putting out more nickel than iron. That's really interesting, really remarkable, and something to be studied in the future. So we're always interested in new ideas. We're always interested in new suggestions, and all ideas are good when they're born. But those that stand the test of time, those that stand up to testing, those that are supported by the evidence, are the ones that survive.
All right, we'll take our next question on the phone bridge, and that one comes from Matthew Glasser with ABC.
Good afternoon. Thank you for doing this. Tom mentioned that the answers will come in time. I'm curious about what are some of the hopes that we might discover from this comet. What might it tell us about our planet, about our solar system, about the universe? Are there key things you're looking for as you start to analyze this data, and are you excited about anything in particular when it comes to better understanding how things are working out there?
Sure, I can take that. Every new object we discover is a new piece in the puzzle. What we're trying to do always is to understand the universe. That's part of the NASA mission, is to understand the solar system, understand the universe, understand the origin of planets, the origin of life. And that is a huge question, and we get little bits, little clues to parts of that puzzle, and we start trying to put that puzzle together. We have gained tremendous amount of information from hundreds of years of astronomical observation and from decades of in situ spacecraft observation has revealed our planets as actual places, not just points in the sky that you could barely see with your own eyes. We've learned about comets and asteroids, and we're beginning to put together a picture of how all of those planet-forming minerals and planet-forming ices came together to form our planets, and how our solar system changed over time. Just one example, we get a fascinating clue from the objects like Pluto that we've been discovering since the 1990s, the trans-Neptunian objects. The way they are distributed through space in the outer solar system show us clues to how the orbits of the major planets may have changed over time in the early solar system. A fascinating thing, and questions that we would never have thought to ask before we knew about these trans-Neptunian objects. Now, interstellar objects, like I said before, are new windows, and it's windows that we've never even looked out of before. So what we're going to find is way too early to predict, but I think we're getting a hint of the breadth, the wide spectrum of conditions that existed in different parts of the galaxy, in different solar systems, where the compositions, the elemental abundances, the mineral abundances may have been very, very different. It would be a different picture if we were seeing the first 3 interstellar objects and we'd say, gee, those look exactly like our homegrown comets. That would have been really interesting, and we would have said, well, maybe our galaxy is a boring place because every place is the same. What we're seeing with this is not every place is the same. That's a good thing. Lots of places to explore, and they will be different if we ever manage to get there.
Yeah, I think of these as frozen fossils from their moments of formation, including the things in and out from beyond our solar system. Or in some cases, we point our telescopes at other debris disks, which is just a whole system full of these small bodies. And so now what this will let us do is tell that story in a broader context between the detailed and large library of data we have on those origins of our own solar system, and how volatiles were delivered to make life possible here on Earth, combined with that big picture of other systems, of the dust spread throughout those other solar systems. And now with this visitor that got frozen in time from somewhere beyond our solar system, and that small picture of what that is like when that formed.
And the fact that, I love the sort of thought of it as that frozen fossil, almost frozen time capsule. We're kind of privileged. I mean, it's come into our solar system, our sun. We know, we think it hasn't seen a star for a long time. So it's actually warming up and giving us more information. It isn't just about a frozen object coming through and us sort of saying, oh, look, there's a frozen object moving through. But as it's almost waking up and showing us its composition, and that's allowing us to be able to do this great science. If it had just remained frozen all the time, we wouldn't know much about it. But it is the sort of its rendezvous with our star that is allowing us to really do this amazing science. And that to me it makes me feel almost privileged to actually be able to unlock the secrets as this cometary object is coming around and rendezvousing and interacting with our solar system.
All right, let's head over to social media. Nina on X asks, will it hit any planets in our solar system?
No, it will not. I think if you, obviously we're not going to run it again, but please, go online, take a look at go.nasa.gov/3i-atlas and take a look at the trajectory. I kind of talked through it briefly. Tom talked through it, and you can sort of see where those planets are. And remember this, even though it's exciting and it's coming through, space is huge, as both Sean and Tom talked about. And so the probability of it actually hitting anything is super, super small. You have to have all these things aligned to actually be able to do it. But certainly the objects in our solar system will be just fine.
And we have another question from social media from Astronomy. They ask, what makes Comet 3I Atlas so different and intriguing compared to the other interstellar comets?
Tom, you want to take that?
The other interstellar objects, we say interstellar objects because not all of them were comets. So the first one was discovered in 2017. That was 1I, Oumuamua, that behaved very much like an asteroid. Again, a little bit like 3I Atlas, a very interesting asteroid, in some ways different from the asteroids we're accustomed to seeing in our solar system. For one thing, it was seemed to be very, very elongated, and while it was inactive, it seemed to be an inert, mostly rocky object. It did show indirect indications that it was evaporating gases in some way. It wasn't around long enough for us to get really, really comprehensive long-duration observations and understand exactly what it was doing. It was the very first one. We saw it for a short time when it was on its way out, in fact, and so we didn't get a great view of that. The second object, 2I Borisov, discovered in 2019, behaved, it was a comet. It was definitely a comet. It behaved in a lot of ways like our homegrown solar system comets, in many ways like 3I
Hi, thank you. This is for Tom and Nikki. One, of the measurements made so far, what is uniquely different about this comet, other than the trajectory, of course? And two, since perihelion, it looks like there are multiple jets. I was wondering if you could talk about that and the speculation that it might have exploded. Thank you.
Go ahead.
Yeah, thanks, Ken. So some of the differences I already mentioned is the ratio, the carbon dioxide to water ratio, the nickel to iron ratio. Also, there were ground-based observations noting that the polarization of the light reflected off the dust was also unusual, so that's telling us some interesting things about the dust. There are other indications that the physical properties of this dust, maybe the grain size distribution, right around the time of perihelion, when it's being warmed most intensely, is something that happens frequently. That's something the comet observers are going to be very, very excited about. It does take some time to figure out, because it takes time for the actual event that happens on the surface to propagate out to a distance where you can see it with the telescope, but people are going to be mapping what jets there are. It doesn't necessarily mean there was an explosion. Jets can also just mean there are particularly active areas on the surface of the comet where more volatile stuff is evaporating in that one spot than elsewhere and jetting out. We saw this a decade ago with the ESA Rosetta mission at Comet 67P. It got up close and personal with the nucleus and saw frequently that there were jets coming out from specific places on the nucleus of the comet. So that could very well be what's going on here. Can't tell for sure, but that's the sort of thing we've seen before.
The other thing I just want to say that we're expecting to see as more stuff gets thrown off this comet in these jets is at those warmer temperatures, additional things can bake off of it, additional gases can bake off, and so we do expect the composition of the coma to potentially change, or those jets to change over time. And looking at the details of what other molecules we detect beyond the carbon dioxide and water we mentioned is also going to be interesting, especially for that sort of like, what was the area in this, what was this stuff made of in the area it was made, like long time ago.
Right.
Our next question is from David Chandler with Sky and Telescope.
Yes, a couple of things. Have you any of these observations showing you anything about any non-gravitational accelerations at this point? And also, can you say a little bit about coming attractions? What observations are in the pipeline that have been made but not released yet? I think the MRO high-rise observations, has that been released yet? And what else is there that's either in the can and waiting to come out, or observations that will be made over the coming weeks as the object comes closer to Earth?
Mm-hmm. I can answer some of that about the non-gravitational accelerations. This is something that we look very closely at for every comet, because that's always something that happens. And just to back up to explain what the question is that as comets evaporate, they are blowing off gas, they are blowing off dust, and every time something gets pushed off the comet, that acts like a little rocket engine at that moment and pushes in the other direction. And so it's very, very common to see comets have subtle changes in their orbits as a result of these little rocket forces, just called non-gravitational accelerations. So this is being monitored very closely. I spoke to our orbit determination team of the Jet Propulsion Laboratory earlier this week, and what they said is that this is being monitored. There are some changes to the orbit, but the uncertainties are still fairly large. It's difficult because we can't see the nucleus directly. It's difficult to get a very, very precise track on exactly where it's going. But so far, the non-gravitational accelerations have been very much on par with the sort that we see in solar system comets.
In terms of future observations, this is a situation where, because this is only the third time we've had an opportunity to look at an object like this, everyone that is in control of a telescope wants to look at it because it's a fascinating and rare opportunity. I know that our colleagues from the Keck Observatory have looked at it. I believe that we're going to look at it again with JWST in December. We have some other ground-based facilities that are giving us additional compositional information as those additional molecules bake off of 3I Atlas. Those are the things I'm aware of. There's probably a lot more that I'm not, because like I said, like every astronomer wants to get data on this thing because it's such a rare opportunity.
Yeah, and the high-rise image that you asked about specifically, Amit kind of rolled that out at the beginning. So please take a look at that image. I think Sean is not bragging a lot on what these astrophysics telescope. I don't know why, but because we are able to look at it in infrared with the James Webb Space Telescope, that will be the last time we can see the comet. So as it is exiting the solar system and getting further and further away, the James Webb Space Telescope will actually be able to track it longer than anyone else, partly because of its ability to kind of look long and deep rather than sort of across and wide, and the fact that it looks in the ultraviolet, in the infrared, so it can kind of see the dark objects. And so I'm really excited about just sort of, tracking it to the very end. Also noted, we're downlinking data from missions. I mentioned Parker Solar Probe because I just heard before we came on that we'd got some data and we'd seen the comet. I haven't had time to look at the data yet, but all of those things are coming up as we are getting more and more data coming down to us from those missions. And then as both Sean and Tom talked about, just really making sure we're sharpening up those images and really making sure they're calibrated. Right now we're putting out almost the raw images. We're putting out things quickly so everyone can see them, but we'll take some time and do some real sort of deep looking into those and do some more of the spectroscopy. Tom showed a really great example of kind of looking through the atmosphere of Mars, take out that hydrogen, take out the hydrogen from our solar system, and then let us look at the hydrogen that's coming from the comet. So we'll be doing a lot more of that as we move on to do great things with NASA science.
All right, that's a great lead into our next question on social media. Elijah on X asks, what kind of processing were the images subjected to and why did they need it?
You want to take that?
The images that were released received the sort of standard processing that we do between the raw data that comes down into a telescope. That, as Nikki said, we need to make sure for scientific accuracy that they're calibrated against the other observations, and we account for anything that the telescope is doing in that moment. And so that it would be our standard set of calibrations and normalizations for a object of this type, which is to say a comet.
I can add a little bit more to that. As Nikki said, our desire was to get these images out to the public as quickly as possible, and so there are some image artifacts in there that you'll see, and I can speak to the Lucy image that you saw previously. If you look at the comet, you'll see some blobs around the comet. The little blobs, faint blobs around the comet are not real. It came from the fact that in order to get this particular view, it was necessary, which is this backlit view, the team had to turn the spacecraft to face more toward the sun than it generally does. And so that means some part of the spacecraft were in the sun, and some of that bright, the sunlight reflected off parts of the spacecraft got into the camera, and that resulted in those little blobs. So that's an example of processing that has yet to be done to figure out exactly what that scattered light contribution was and remove that from the image so that what we show in the image is entirely what was there in the sky and not something just made by sun glints off the spacecraft hardware.
Yeah, and sometimes I think you showed the SOHO image where we actually stacked a couple of images, because a single image you wouldn't be able to see it would be too faint, but if we stack a couple of images together, then you can actually start to really make out what that comet looks like.
Okay, next, Gail on Facebook asks, how can an object like 3I Atlas come from so far, moving as fast as it is, and not hit anything?
Orbital dynamics and space is really, really huge. And so, you know, it is amazing to think about just how big even our solar system. And so to give you the Voyager spacecraft, Voyager 1, is now 1 light day away from Earth, which means when we send a command or we send a photon from Earth, it takes a full day for that photon to arrive at Voyager. And Voyager is only just outside kind of what we think of as the edge of our solar system. And so space is vast. Yes, this thing is moving quickly, and yes, it came from outside our solar system. But you know, the probability of it actually hitting something is so small, because everything has to align. It's also not quite in the ecliptic plane. It's not quite in like our normal. If you think about sort of looking side on at our solar system with the sun, and then you put the planets kind of in a row. Normally, everything sort of orbits in this plane. This is slightly tipped. Not unusual because it's not gravitationally bound to our sun, but it's slightly tipped. That makes the probability of it hitting it almost even greater.
If I can play with a scale model solar, if you make a scale model solar system where the sun and the Earth are 1 foot apart, that's about 1 foot. The sun is a P. The Earth, you need a magnifying glass to see, it's so small. The entire solar system will just barely fit in your house if you squeeze a little bit, and the next nearest star is over 50 miles away. So they call it space for a reason. Most of it is space.
Okay, we'll head back to our phone bridge. Our next question is from Brandon Spector with Live Science.
Hi, I wanted to ask about the age of the comet. You mentioned there's circumstantial evidence that it's much older than our solar system, but how can we constrain that age a little more? And what will that tell us if it is indeed much, much older than the solar system?
I can start that, but I'm going to pass it to Sean to talk about ages in the galaxy.
Okay.
So, cutting to the end, the bottom line is going to be, it's probably going to be really hard to get a more precise figure from one object. I think what we're looking at in the future, as we discover more of these, when we get to the point where we have maybe a few dozen of them and look at the distribution and properties, we may be able to get a better handle on what the distribution of ages is. So what's going on here is that it takes the sun 240 million years to orbit around the center of the galaxy, and we're doing that with a neighborhood of stars. So we're all going around the center of the galaxy. The relative motions between stars in our solar neighborhood is sort of 10-ish, 15, and sorry, I have all these numbers in my head in metric because that's the way I learned them, but 10 or 15-ish kilometers per second. So what is that? That's about 25,000 miles an hour, I think. And 3I Atlas is coming through at a speed of 60-something kilometers per second. So that's 3 times faster than the average of our local neighborhood, which is telling us that it's coming from a different population from what we have generally around us. Now, Sean will be able to clarify the age dispersion relation in our galaxy, which tells us, which has been discovered over the last century studying stars in the galaxy, that the relative speeds of stars is an indicator of age. Stars that formed older in our galaxy over time increase their random motions for reasons that Sean will explain. And so that's the circumstantial evidence that makes us think that 3I Atlas came from a solar system that had larger motions relative to our solar neighborhood and is older. But it is a circumstantial and probabilistic argument.
So I'm just going to take this opportunity to brag about our telescopes and the James Webb Space Telescope in particular.
Go for it.
This blows my mind. We have data from galaxies closer to the origin of the universe than we have data from rocks closer to the origin of Earth, right? In other words, like if you pick up the oldest rock that we have from Earth, it is further away from the origin of Earth in terms of hundreds of millions of years than the amount of time there was between the origin of the universe and the earliest galaxies that JWST has now observed. And that's part of this story of how well we understand not just the history of our home planet, but the history of the entire universe that it's a part of. And now this is just another part of that story of the local neighborhood that our solar system is a part of.
All right, our last question for today comes from X and asks if we can see grains of sand on Mars. How is the clearest photo we can see for 3I Atlas what we've seen?
So because we're closer to the grains of sands on Mars, right? And so the JWST can only get like these single pixel blobs of the faintest galaxies, the furthest away galaxies in our universe. And because 3I Atlas is in our solar system, we can get the images and the compositional information with JWST. As it got closer to some of the planetary spacecraft Tom was talking about, they can't even see these galaxies, but because 3I Atlas was closer to them than they were to JW, they got really good images of the object as it passed by.
Right, as you said, we can image individual grains on Mars because we have spacecraft standing on Mars.
Right.
But even our closest spacecraft to 3I Atlas, we're still 19 million miles away.
And it's going too fast for us to send something there to intercept and get that close to it. So that's just not, that we just don't have the, if we could, we would, we would be there up close and getting those grains.
All right, well, that's all the time we have for today. Thank you so much for joining us. Be sure to follow along with NASA as we continue to observe 3I Atlas. Find new images, detailed information, and resources by visiting go.nasa.gov/3I-Atlas and by following NASA Solar System on social media. Thanks for joining.
you.